Shall I start? Okay, very good. Okay, so I hope I gave you an overview, and it was very dense, lots of things in it, but don't worry, we will go back to many of those. And thank you for your beautiful questions. So now we go back to the basis, but I thought it's always good to give a kind of like a view from the top and then go into the details. So now there will be lots of writing on the board. I don't know if you're used to it, but I like personally to do things step by step, and I like seeing them written on the board by the lecturer rather than flashed through the slides, because sometimes slides are a bit too fast for me. So I hope you don't get too bored. But I really want to show you things that you have seen already in some other lectures, but I'm not sure that you have seen their derivation. If you do, you can look at your laptop and other things. But anyway, so the historical overview, that I think it's really a fascinating story about the proton structure. It was thanks to the collider we had at SLAC. So we, in 1955, Hofstadter et al. Observed the first deviation in the scattering of the electron of proton from a simple point-like Mott scattering. That is where it was realized experimentally that the proton had an internal structure. It was not an elementary object, okay? And that was the very famous paper, and that the kind of laboratory. It was really looking at the angle of scattering of the proton that deviated from the Mott curve. That is the one that you see at the bottom. There was this deviation in the tail. And then it's interesting because theory and experiment developed in parallel. In the meantime, in 1964, Zweig and Gelgman independently postulated the existence of three aces, how Zweig called them, or quarks, Gelman, that had a fractional electric charge. There was really something amazing because, you know, people thought that everything was quantized in terms of the electric charge, so it was something smaller than it. And spin 1/2 to explain another thing, which was the proliferation of mesons and baryons that were observed at colliders. So everybody was happy with proton and neutron being the elementary particles, and then suddenly they saw lots of heavier cosines of proton and neutrons, tens of those. So they thought, we cannot have a theory that is so complicated. You know, somehow the truth must be simple. Okay, so there must be something behind that, a structure that is much simpler than all this stuff that we are observing now. And they came up with this theoretical model. Then I think quark was the popular word that have been called that. But they didn't believe that these things had a kind of physical reality. So they thought it was more of a mathematical model rather than particles. Because the question is, what can bind together these particles so well that the proton doesn't decay, you know, that it's united. And it was in 1967 that there was the first deep inelastic scattering experiment observed at SLAC that actually gave the evidence of the existence of these point-like particles that had spin 1/2 that were the elementary constituents of the proton, that only 3 years later were identified with the quarks that were modeled theoretically because of geometrical intuition of Gelman. So I think this is one of the beautiful examples where theory, if you want an aesthetic perception of reality based on some artistic view or in a symmetry, you know, somehow meets the experimental reality, and together we can do a step forward in the understanding of nature. So I first want to, how do I do? Okay, I write it on the board, but for those who are on Zoom, things are also on my slides, but now I will write them. So the first thing I want to show you is that in general, okay, after the experiment in 1955, when they realized that the proton had a structure, how did they parameterize the structure? So you know really well the final answer is the scattering of an electron of a proton can be parameterized in terms of the structure functions, okay? And then the structure functions ended up being simply the sum of the Parton distribution functions. So this is already the end story, but I don't know if you've ever seen the details. So in the next 20 minutes, I want to show you the details. So how do you actually do this mathematically? How do you parameterize in terms of the structure function, and how the structure function are flat with the scale as it was observed at luck. Okay, so I will do it on the board. Please interrupt me because my handwriting sometimes can be really horrible. So if you don't see what I'm writing, tell me and I will rewrite nicer for you. Okay, so the problem now is that we are doing some experiments and we want to parameterize what we observe in terms of some experimentally observable quantities that we want to measure to understand what the proton is. So put yourself in the 50s and let's go back. So how did we do? We had the Feynman rules and all the things that you study in quantum field theory. So imagine we have an electron of momentum k plus a proton of momentum p. They go into another electron of momentum k prime plus x. Okay, so it means that the experimentalists, they integrated out all the other stuff that came out of the collision. Okay, so this is what it means, plus x. They only observed, so they classified as event anything that had an electron in the final state. That's it. They didn't observe anything else. Okay, so let's do it. This is a QED process. So you have an electron that goes into another electron. You have a scattering of, at the time at SLAC, we were at energy much smaller than the Z and the W. So there was only a photon here, a virtual photon. They didn't have enough energy here with the electron to create a virtual Z or W. Okay, so we can, for the moment, let's just have this. This hits the proton that I just draw as a bubble because we don't know what it is made of. I only know that it's not an elementary particle. And here I have another line. So this is the proton, momentum P. And here is the other stuff that I don't care about, okay? So this is really the leading order diagram in QED. Okay, and then let me just write the kinematic variables. So we have the center of mass energy, which is P plus K modulo square. So these are all the four momenta, okay? I'm writing the relativistic momenta. And then we have Q, which is the momentum of the virtual photon I have here, which is K minus K prime. Okay, very good. And then I'll give you an exercise for those of you who want, and in the slides there is the solution, what happens when you add the Z or the W, okay? But it's the same derivation. Okay, so from this Q, we like to define other kind of Lorentz invariance quantities that do not depend on the frame. So usually you have Q squared, which is minus the virtuality of the virtual photon, so K minus K prime modulo square, that is equal to 2K dot K prime. We are ignoring the lepton masses. We just have, so I'm ignoring K square and K prime square because the masses of the leptons are much smaller. Do you see it here? Okay. And for example, in the rest frame, so just to say that this in any frame, so in the lab frame, for example, this is the energy of the initial electron, the energy of the electron that you scatter off, and 1 minus the cosine of theta, which is this angle between the beam line, okay, of the proton and the electron that comes out, okay, is the line between the outgoing electron and the incoming electron. Another variable that you will see a lot that comes just from the kinematics is XB, the Bjorken X, which is Q squared divided by 2P dot Q. Okay, the P is this, Q is this, okay? So it's, yeah. Let's just call it, and we know that XB must be larger than 0, no? And then another variable that is interesting and is measured experimentally. Again, you can write this in terms of the energies, just energies and angles. So everything here can be written in terms of energy and angle. And then there is the inelasticity, which P dot Q dot P dot K, which is just, if you write it in terms, in the center of mass energy, is 1 minus E prime divided by E. So it's the energy transfer from the electron to the proton, okay? And this is clearly between 0 and 1. And then another interesting thing is the mass of the thing that you ignore. The mass of the things you ignore is just P plus Q squared. And this can be written like the mass of the proton squared plus Q squared minus X divided by X. And from here, XB, sorry. And we know that because this is larger than 1, the Bjorken X has to be smaller than 1. Okay, so we define two variables, the Bjorken X, and then you will see why it's important, which is between 0 and 1, and the inelasticity, which is between 0 and 1, and 2 Q squared and MX squared, okay? And then we have two regimes of scattering, which is the elastic limit, which is when basically mx is just equal to the mass of the proton. So nothing happens. The proton doesn't disintegrate, it just stays a proton, okay? It's just hit and goes out like itself. So this is the elastic limit that we always ignore. So there are other kinds of experiment, which is not this experiment. So this kind of events, so this is when xb is equal to 1, okay? And then there is the limit that we care about, which is the deep inelastic scattering. Inelastic scattering, which is when mx is much larger than the mass of the proton, okay? Which is basically the limit of large Q squared for a given xb, okay? It means that really you produce much more stuff than what you have at the beginning. So the virtual photon goes deep into the proton. Okay, so here is just the kinematics. Okay, now I have to, how do I do? Okay, tell me when you finish writing and then I write the next board. So you always do the kinematics and then you write the Feynman diagrams. It's there, exactly. So in fact, let me, you can keep that. Okay, fine, good. Okay, now how do you write the cross section for this? You factorize, no? Again, the magic thing. So you have the diagram there, so I can cancel it because otherwise we don't have space. So how do you write the amplitude for electron proton into electron? So actually here I'm doing something cheeky because I want to help you for the exercise. Okay, let's say lepton proton into, okay, I'm just saying that the lepton doesn't have to be necessarily the electron. It can also be an electron that becomes a neutrino or a neutrino that becomes an electron, because I want to make it general for when you have to do the exercise with the Z and the W, okay? Very good, but so the beautiful thing is that the amplitude factorizes, so you can write it like, so this is the scattering elements of what happens at the bottom, okay? So remember you have this thing. So this is the J, the current of the interaction that happens, sorry. So this is this interaction here, no, of the two of the lepton with the QED current, J mu. And then you have the coupling of the electron, of the lepton 1 with the vector boson. Again, let me call it V star instead of gamma star, because you can have also W and Z. And then you have the propagator, which is minus eta mu divided by Q squared minus the mass of the vector boson square. So 0 in the case of the photon, and Z or MW in the case of the Z and the W. And then you have the coupling of the proton with gamma, with the vector boson, and then you have X, J mu P, okay? So and where J mu is still the QED current. Okay, very good. And you know, but anyway, it's written in the exercises that this coupling over here, you know the Feynman rule, no? So if you have V, and here you have L prime, the Feynman rule is the minus I E K V gamma mu, and then you have the vectorial coupling plus gamma 5, the axial coupling, okay? And then you have a table in my slides where you say exactly what is V and A for the W and the Z, but okay. For the photon, you know that there is no axial coupling, it's just V, which is equal to 1, okay? Very good. So now let's compute it. So given the ingredients, given that we can factorize that, we can write from the amplitude the differential cross-section. So what is the differential cross-section for a lepton proton going into lepton plus X? So that's the usual cross-section formula that you have, is 1/2 times the center of mass energy. Then you have the amplitude element square. So you have GLV GPV modulus square divided by, let me write Q square like minus Q squared, the variable we had before. So this is just Q squared plus the mass of the vector boson squared. And then you have L mu nu, W mu nu, 4 pi, d3k prime divided by 2 pi to the third 2e prime. Okay, so it's the phase space of the only particle we observe, which is the electron in the final space. This is the matrix element square, and this is 1/the flux, no? of the collision. So let's write these 3 bits in turn. So number 1, number 2, number 3. So phase space, number 1. You want to write this in terms of the invariant that we have measured before, because these were the variables that the experimentalists used to measure this event. So you want to make a change of variables between the energy and the angle cosine and the Q square X mu quantity, and that's easy. You know how to do it. I feel bad at writing to you because you will know it much better than me. When you write it, if you integrate over the azimuthal angle, this is E prime, d E prime, d cos theta. Okay, that's just a change of variable. So, and then here you have to do a bit of more manipulation. I did it explicitly in the slides, but I don't do it now because it's boring. This can be written in the end like y squared. Can be written like Q squared divided by 2sxb squared 1/8 pi square, and then the x, it's just a change of variable, okay? You have to do the Jacobian. Okay, so that's the first bit that we need to write the cross-section. And then we need the other 2 bits, okay? So the leptonic tensor, it's easy. So what is it? We write it just like the amplitude that we wrote before. No, is this L prime. So is you have the normalization factor 1/2 L J mu complex conjugate L prime, and then you have L prime J mu L. And we know that we can compute those as the trace over the amplitudes, no? So you have, so from the Feynman rules that I wrote before, here, you know that each of these current is given just by U bar, K prime, so the outgoing lepton, and then you have the vertex minus IE coupling strength, gamma mu V plus gamma 5A, and then you have U of K, okay? The spinors, U bar, you know them. Good, so when you put them together here, you're taking the trace over U bar, blah, 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 and the vertex, okay? And that's something we can do. So if you do take the trace, so you get something which is proportional to the trace of K bar. Let me call this gamma mu K prime slash gamma mu, sorry, gamma nu. And be careful for the exercise number 2 that you have to think a bit whenever you have a neutrino or antineutrino, these two can be swapped, okay? So, but okay, this is, I think, okay for when you have an electron or neutrino, you swap the two if you have an E plus or antineutrino, okay? It's just because the arrows goes into the opposite direction when you write the trace, no? If you have U bar. Okay, very good. So this one, when you do the trace, becomes equal to 2 times K mu, K prime mu, plus the two swapped. And I hadn't done a trace for ages, I realized when I did it for this school. So you might get rusty like me, but okay. Q squared divided by 2, eta mu. And then again, that's something we don't care now, but for your exercise, if you have also the axial bit as you have for the W and the Z, you have an extra bit here, which is plus or minus I, a coefficient that I'll tell you in the exercise, and then you have epsilon mu alpha beta, K alpha, K prime beta. This is the Levi-Civita symmetric tensor, okay? Good. So we are done. Now, what do we have for the W? So the W, we have to parameterize the unknown, okay? We have to think, how can we parameterize the unknown scattering of a photon with an unknown composite object, which is the proton, okay? We still don't know what it is made of. So let's first write, can you see if I write below here? At the bottom, can you see if I write here? W mu. So first of all, let's put in here all the bits that you didn't see there. So it's, again, there is a factorization 1/2. I don't know why they do that, but okay, it's a convention. So 4 pi E squared. So they take out the electric charge of the components of the proton. So people always write a 4 pi here and a 4 pi there, which I don't know why they do it. And they take away the electric charge of the component. But okay, we can live with that. Convention is convention. We weren't there to write the rules ourselves because we were too young. Me too. So you have the sum over X, and then you have the matrix element of proton, QED current, because we know it's a QED current, X, J, mu, sorry, this is a bar, P. We integrate, so we sum over all possible X states. That's what it means to integrate it out mathematically. And then you should have told me, where is the delta function in the final space? You know, you have a delta function, I put it here. So delta 4 P plus Q minus the momentum of the stuff I'm ignoring, which is Px, okay? So it has to disappear with the delta function. Very good. So this is the general structure, but then you have to think, how can I write something I don't know? So you parameterize by adding all possible 4 vectors that are Lorentz invariant, okay? So you only have 3 things here. You have Q, you have P, what's the third? No, that's it. You only have P and Q, okay? So you only have P, Q, and you have the tensor. So the Lorentz tensor, so eta mu nu, which is 1 minus 1 minus 1, and then the anti-symmetric Levi-Civita tensor, epsilon, alpha, beta, mu nu, whatever. So we have to be creative and think, what are all the possible Lorentz invariant structure? And then you parameterize them with something that depends on the 2 kinematic variables that you have parameterized the phase space with, okay? So, can I, okay, let me write it here. So let's do this effort of imagination. So you have W mu nu. So the easiest is eta mu nu with F1. So this is a coefficient, as I said, that can only depend on X and Q square. The 2 variables of the phase space that we left out, okay? Then what are the other possible structures? Okay, we have these, P mu, because we like it. So it's P mu, P nu divided by P dot Q. Again, it's a convention, it's a coefficient. You can do whatever you want, but it's a profound thing. And then you have F2, so another coefficient. And then you have the again, let's do P alpha, P beta. Because the antisymmetric thing, you also have this stuff, P dot Q. And then you have epsilon, alpha, beta, mu. And F3. So you see, so far I use P and all the possible tensor, and then I need 2 more, but they will disappear all. But okay, let me just write. So there will be something which is proportional to F4 plus I F5 P mu Q mu. Another combination with the same thing. And then you have something proportional to Q mu Q nu. So, okay, these are all the Lorentz invariant, nothing else. You can write linear combination of those, of course, but nothing else. But time reversal, so if you impose that the tensor is the same when you send time into minus time, then you get rid of these. So time reverse, so basically a CP invariance, no? Reversal, it kills F5. And then you have the conservation of the electromagnetic current. You remember the usual thing that you have now have yes, so the thing that you always have whenever you have the amplitude, that Q mu, W mu nu is equal to 0, okay? Whenever you go on shell with the photon you have. And this thing kills other combination. So this thing, you kill F4 and F6 equal to 0, okay? So what happens when you impose these things, that your Lorentz structure becomes written as and also because of that, you have to recombine a bit these two coefficients, but okay, you do it. And you get, can I erase that? And you get that you can write these unknown things in terms of very precise Lorentz structure, so minus eta mu nu plus q mu q nu divided by q squared f1. So you absorb, this is wrong. So it's so they have to become, it's not zero, but they have to become proportional to f1, f2, okay? So I did write something stupid. But okay, so if you impose that, you can see explicitly that you only have a linear combination of f1 and f5, 4, and f2 and f6 that survive, okay? In fact, this one goes in here. F1, so basically, yes, these two, you identify the two and they go together with the same coefficient. And then you have plus p mu tilde divided by p dot q f2. And then you have plus I epsilon mu nu alpha beta p alpha q beta. And the F3, okay? Very good. Where P tilde is the shifted momentum. Okay. So just to say that things, so the Lorentz invariance and the word, that's the name, the word identity, now I have it, impose some particular combination of the momenta of the things you have in front of the parameterizing functions, okay? But the beautiful thing is that when you put together the lepton tensor and the hadronic tensor, you have to contract explicitly these momenta over here with this combination of momenta. You can do it. It's done in the notes that I'm going to post later. And then the whole structure simplifies a lot and becomes quite nice, actually. So then it's just a kind of Lorentz momenta product. And when you put it together, yeah, maybe it fits here. So you have, so if you put 2 plus 3 together, the two formulae that we wrote here, so that's number 3, that's number 2, so 3b's. And then you get that L mu nu, W mu nu, so you contract the indices here, it's equal to, you always write the 2q squared divided by y squared, the inelasticity, then you have y squared f1 plus 1 minus y f2 minus plus, depending on neutrino and antineutrino, c lv x Bjorken y minus y squared over 2 f3. Okay? So beautiful. It means that if you measure experimentally the y, q square, and xb, so they're not independent, xb can be written as a function of y. Anyway, so you just have to measure two objects experimentally. Yes?
The derivation for the hadronic tensor, at one point you insert fleetness in some of the complete set of final states for the hadron. Does that have any impact on why experimentally you only measure the electron and not the X? Because
yes, exactly. So if you don't sum up over that, you would have so the condition that you put on the generical structure are more complicated in the sense that you have, I think, more Lorentz structures that than the one you write there. So I think I did see it done only once in my life, because they always somehow, when you do deep inelastic scattering, you only integrate over that. And this is what, you know, because you integrate over the X, then you can write the most generic Lorentz structure, and then you can apply time reverse, and then you can apply the word identity, and everything seems fine. So for example, the thing that you cannot apply is the word identity, because I think if you, yeah, it has to be done on an inclusive final state. So I think that's how but to be honest, I've seen it only once and I don't remember really well, but that's a good question. Okay, so the trick, what the experimentalists do, now I go back to my slide for a second, they measure for each event this thing, and then they extract the F1, F2, and F3 factors, okay? So you have to put all the events together, parameterize the kinematical structure in this linear combination, and extract experimentally the form factors. And then based on that, they learn what the proton is made. So let me just, okay. So this is how it can be parameterized. So I forgot to say that when you put it together into the final formula that of the cross section, that's what you get. No? So you have these coefficients and these combinations of kinematic variables. If you want to have a second to write them, I'll let you do it. But okay, so the surprise was that when they were extracting the F2 bit, that was the slack measurement, that this was not depending on the Q-square scale. Okay, so these coefficients were flat with the Q-square, with the transfer of the momentum of the virtual proton. Okay, and also the F1. F3 was not there because we didn't have a Z or W exchange. It was only the photon. Okay, so in that case, F3 was equal to 0 because we didn't have the axial charge. Okay, so this was demonstrating that the exchange vector boson was scattering of something that didn't have an intrinsic energy scale. So something that was point-like, like the partons. Okay, so it's as if really the lepton was scattering off charge spin 1/2 constituents that were carrying a fraction of the proton. But again, this is something that you always read. But if I have 2 minutes, I show you how you prove it. Okay, so let's say if you do this assumption, do you actually find F that do not depend on Q? And that's something you can see it explicitly. So let's say that what happens if we now assume that, do we find mathematically that this function F1, F2 do not depend on Q squared? And the answer is yes, because then everything becomes really simple, no? Because the hadronic tensor that we wrote here can be rewritten in a very simple way, because at this point, so let me just cancel this, because I think I only need one line. So when you put it together, what is the Parton model assumption? To do that, I need a space here. So the Parton model assumption is the following. Is that the sigma, so the Partonic cross-section for L, P onto L prime X can be written like the sum over I, where I goes over all the partons of the proton, of the integral between 0 and 1 of dz of Fi z d sigma hat I z p. Okay, so what is it? So what the Parton model is telling me is super simple, is that the total cross-section that I wrote before can be written like the sum over some I, which runs over all partons that are inside the proton, that carry a fraction z of the proton momentum of the cross-section for the scattering of this point-like object against the photon, okay? They are spin 1/2. Okay, so this cross-section is nothing but sigma hat of lepton of, let me call it pi of Lx, okay? So I'm basically summing up over all the partons, the partonic cross-section, okay? Times the probability that it exists a parton I that carries a fraction Z of the proton momentum, okay? So I'm saying that this complicated thing here can be written like the sum over Fi of this thing. So where this is Pi, and again here you have anything. So in this case, X is like all the other possible partons, no? So you're also partonizing if you want the final state, okay? So you're saying that all this stuff is simply Fi of Z, Pi, which is equal to ZP. Yes?
So did this interpretation come after the experimental data?
After the experimental data. So at the beginning, so now we did the journey of, okay, let's imagine we just did the first experiment in 1955 and we are ready to do the experiment at LAC in 1967. And first we have to do a theoretical effort to parameterize the experimental result in terms of some functions. The functions surprisingly came out being flat, so they didn't depend on Q. As a result, this model was cooked up. So there is no intrinsic scale. It means that there is no extended object, but everything is done by tiny particles that are point-like. So, and then you say, okay, now what happens if I plug this model into my old derivation before, okay? So this is something that I did in the notes, and you can follow through and I can talk to those interested this afternoon. But the interesting thing is that now this bit is extremely trivial to calculate. Because this, again, when you look at, if you want, the hadronic tensor for each of the parton, this is a QED current, like the one we calculated for the leptons, okay? So this W hat is, again, just equal to 1/2, whatever, E squared, and then you have the trace over, you know, like, let me call it Pi gamma mu P prime of something gamma nu. So this bit that before had all this structure function, now we don't need it anymore because we don't have any structure function anymore. So we just write it like the trace of a QED amplitude of fermion, which I parameterize in all. So this trace comes from U bar gamma mu U times E. So if you plug it in, I don't want to do it because it's simple algebra, and I did it in my notes here, so you can go through my slides and do it yourself. But the beautiful thing that you find is that you plug this thing into our formula, okay, and you find that the structure functions are just equal to, so it's not magic, it just comes from the same procedure we did before. F1 of X Q squared is just equal to 1/2 sum over I of EI, the electric charge of this parton, times Fi of X. And F2 of XB Q squared is equal to the sum over I of EI squared XB Fi XB. So something that was very complicated, that could have been very complicated, is very simple. But I want you to stop for a second and be surprised by something. So the XB here that I find when I plug it into my computation of the structure function is the Bjorken variable that we defined in terms of the hadronic final state. So this is a macroscopic variable that depends only on the things that come out of the scattering, okay? So you have the angle, the energy, and blah, blah, blah. This is the argument of the Parton distribution function. So this model is surprisingly simple because the fraction of the proton carried by each of the parton is nothing but the Bjork NX. So I am measuring, when I measure the angle and the energy of the final electron, the exact composition of the proton, right? So I think this is super unexpected. And in fact, it comes from the delta function that you find so the delta function identifies the macroscopic variable with the microscopic fraction of energy carried by each of the parton. And the second thing, which is very interesting, is that from the structure that you have here, you see that F2 is equal to 2x F1. So this is the Callan-Gross relation that is typical of a particle of spin and a half. Because, and again, that's something that I don't want to tell you now because I would waste the whole time by doing that. But it shows, and I did it explicitly because whenever people said, yeah, that proves that the partons are spin 1/2, I never understood why, to be honest. And I said, yeah, of course it's true. But then I actually did it, and you can do it easily because if you use this and you find the W, the hadronic thing, the hadronic tensor that you get in the Parton model, you see that whenever you take the longitudinal polarization, so you take a longitudinally polarized photon onto your W mu nu, when you calculate this, which is the longitudinal polarization of the object whenever they hit a longitudinally polarized photon, this in the Parton model is equal to 0. So you only have a transverse, okay, which means that you have things that have spin 1/2 that are only, have the up and down polarization. They don't have any, if it was spin 1, you would have a longitudinally polarized Parton because you've got 3 degrees of freedom instead of the 2 of the spinners, okay? So you can, that's something that I explain better in my slides, but this is a profound theoretical consequence of the fact that the partons are spin 1/2 objects, okay? Yes? Exactly. They don't have the gluon. Exactly. That's a perfect question to go to the next bit. So, yeah, this is what I just said. And then I give you, but I'll do it later. So these are the first exercise, if you want, showing the Parton model following exactly what we did earlier, that when you consider a contribution from a Z boson, you have this contribution for the structure function F3. And then there is something about the scattering of the neutrinos that also it's interesting, and we can do together with those of you who want this afternoon, okay? But it just follows the same algebra that I did. And now going back to your question, so thing worked really well. So the Parton model seemed to work perfectly until we had a collider that had a much larger energy. In the meantime, QCD was established, okay? And whenever the Hera collider started, and we had a much larger center of mass energy that came from electron that had 27.5 GeV and proton in the circular collider had 120 GeV of energy, you can see that the scaling that we observed before was only approximate, okay? It was true for Bjork NX that were large enough, okay? Between 0.05 and 0.65. Above that, you can see that there is a violation from the scaling. As you increase Q squared, the structure function actually depends on the scale. And this is beautiful again, because this is explained perfectly by QCD. How? So it's as if that this is the Parton model. Okay, you have just 3 quarks up and down, and everybody is happy because they carry a fraction xb of the Parton. Of the proton's momentum. When you start adding QCD, increasing Q, more things happen. So you start producing gluon, producing pair of quark, anti-quark, and everything happens inside the proton, okay? But this is a pictorial view. How do you understand it analytically? Here, I did that. Do you want, let me think. I can either show it on the slide or do it on the board. What do you prefer? Like, who votes for the slides? Who votes for the board? Okay, it's an event, so I have to decide. Okay, let's say that. Let's do it on the slides, and then I just write the important things on the board, okay? I think it's easier this way. So what happens here? So this is the Parton model. It's what I wrote over there, and you have it here. Then you add QCD correction. So to the Parton that comes in and interacts via QCD with the photon, you have to add the real emission and the virtual correction, what we did before, okay? So real emission, it means that this P hat, which is the proton fraction carried by the Parton, becomes Z P hat, because some of its momentum is lost to a gluon that is emitted before it gets to the interaction, okay? So this is the initial state radiation. At the same time, you also have virtual correction that count the same order, okay? So you can have a virtual gluon that is then reabsorbed before the things get into the collision. Very good. So you can do your parameterization, blah, blah, blah. Again, it's just a matter of doing pen and paper your kinematics. You write the quark before the emission of the gluon and the quark after the emission of the gluon. And this is what happens at the hard scattering point, okay? So that's the bubble of the amplitude that has a quark of momentum P minus K that enters, okay? So this is the QED collision, very good. But the beautiful thing is that whatever I say here, and that's a crucial thing, doesn't depend on what happens at the level of the interaction. So whether here then I have the scattering with the photon like in DIS, or whether I have a scattering with something else, everything I'm doing up to the pink bubble is totally independent, okay? This is, keep it into your mind because it's a crucial thing of factorization, okay? Good, so you do your kinematics, and what do you find? Again, you have to do the phase space parameterization. So this is just the phase space of the emission, because, so remember that you have two things. So you have this thing, no? So the proton, that's a Parton model. So this is P hat, which is X Bjorken times P. And this guy emits a gluon, okay, of momentum K. So now the scattering with the virtual photon that produces another Parton here has as momentum X Bjorken P minus K, okay? That's the incoming momentum. Very good. So I have to do, so I already have the phase space that I put into my thing, the phase space of this and that, but now I have to add the phase space of the emitted gluon, okay? So I have to add D3K to pi to the third to EK. Is the usual phase space of the particle. Very good. So this gives me this important factor, which is remember that I parameterize K as 1 minus ZP. So this guy comes in with the fraction Z of the proton momentum. Okay, so I've got two fractions, X from here and Z from the emitted thing. Okay, so I have, here you have X, B, Z, P. Okay. Okay, so from the phase space, you have this factor 1 minus Z. And from the amplitude, you get these other factors. So you have the amplitude without the emission of the photon times this factor, which is universal. Okay, so this factor only tells me what happens in this emission, is the matrix element for this bit over here, okay? Before it enters the amplitude, okay? So you have the matrix element, what I call M1 is the matrix element of this times the matrix element of just the emission, okay? So it's a matrix element of 1, 2, 2. Okay, so one quark that splits into a gluon and a quark. Very good. So when you do that, you find something that when you put in the cross-section, it looks innocuous, but it's not, because it has two singularities. And remember, you never want to have infinity in your computation of physical cross-section. So tell me, if you look at this thing, so this is the cross-section for the usual process when the quark emits. So you have a singularity in z equal to 1, because this is when z is equal to 1 goes to infinity. And then you have a singularity here when kt goes to 0. What is the limit kt goes to 0? So kt is the transverse momentum of the gluon. So kt is like k, if you want, sine of theta. So it's something that goes to 0 as the angle of the emission becomes small, okay? So the limit kt to 0 corresponds to the collinear limit, in which the gluon is emitted collinearly to the parton that has emitted it, okay? And then there is the other limit, which is the limit in z to 1. Remember what was z is 1 minus zp. So z to 1, it means that k goes to 0, okay? It means that the momentum of the emitted gluon goes to 0. This is the soft limit. So we have two limits that are causing us trouble. So one is z to 1 and k to 0. So what do we do? For the limit z to 1, we just put a trig, a factor of epsilon, so it doesn't go to 1. And then we hope that the epsilon goes away, okay? And for the kt that goes to 0, we put a factor of lambda, again, hoping that we can get rid of this lambda that has to go to 0. So the beautiful news is that whenever you look at the virtual contribution, it gives you exactly a contribution of the same and of the same contribution, but opposite sign that kills the z equal 1 singularity. So when you put together real plus virtual, you have that this singularity in z equal 1 is cancelled by this cross section. But anyway, the limit z equal to 1 is cancelled by the virtual emission, because you have real minus virtual. And the virtual, remember, there is no emission because this thing is absorbed back. And so this is, you don't have the z. So you just have xb times p, which is the p hat momentum that we had here, okay? So virtual per real, but we still have this lambda squared that we didn't get rid of. So what do? You do something like you do in alpha s. So whenever you do the integral over the transverse momentum of the emitted gluon, you split it in two. So you split it between the lambda square, which is the singular bit, because I have to send it to 0, and some scale, which we call mu f, and then mu f to kt max, which is the kinematical limit of kt. And this bit is singular, this bit is finite. So what do? Exactly like alpha s, you absorb the finite bit into a redefinition of the Parton distribution functions, okay? So what you're doing is that basically you split the non-singular terms, let's keep them there for the moment. And this logarithm that gives you something that goes to infinity, keep it there, and now you see what's gonna happen. So when we put together the cross-section again, this log that we had, you put it together with the SQ. So basically, your Parton distribution functions have to absorb all this stuff, including the singular bit. So you redefine the Parton distribution function from the bare function which are here to something that now depends on this unphysical scale mu f, which I just put it in to split the integral in two. And at this point, you are done, because if you say now my Parton distribution functions are actually the redefined one, okay, then you have something that depends. So when you absorb all these things, you have the FQ, this one. So you have, sorry, I got lost in my, so you have the redefined Parton, which multiplies a finite cross-section, which is this bit. And you have that the function that you have redefined according to this way. So what do they do? Now depend on mu f from the bare function you had before plus this kernel here, which is process independent, is only purely the collinear remainder of this thing, which has nothing to do with the process. So we never use the process. So the PQQ, the function you have here that you have to reabsorb together to redefine the Parton distribution functions is universal. Okay, so let me find the end of it. So in the end, again, that's something that I can do with you as an exercise this afternoon because it would have taken too long now. But what I did is exactly what I did for alpha S. So you see that you add QCD, it gives a collinear singularity that there is no way to reabsorb. So you reabsorb it by redefining this function f, like f plus 1 bit, which absorbs this logarithm of k squared over lambda squared, plus 1 bit, which is purely a kinematic bit that is universal. And when you do that, then the cross-section is finite because now you have a regular Partonic cross-section in which you don't have anymore the collinear singularity because the bit of the log that was divergence was eaten away by these functions over here. And then the other thing, which I didn't have time to say, is that clearly when you have this, you can also have this. You can also have a starting gluon that gives you the same Parton that then scatters against the photon, okay? So you always have a mix between initial quark and initial gluon that give the same final state. Simply before you had the gluon that splits into quark, anti-quark, and here you had quark that splits into a quark and a gluon. But the quark that comes here is the same guy with the same energy. Okay, so you have two factors, the mixing of quarks and gluons and a dependence on the scale. To conclude, the dependence on the scale is something that in the same way as it with alpha S, you say, if I don't want, because the scale mu f that I added is just an arbitrary scale, the bare things don't have to depend on it, exactly like you do for alpha S, you have a renormalization group equation for these functions. So you can tell that this function, actually you have many quark, anti-quark, and the gluon, they're all coupled up together. So you know that as you change mu square, so t is just the logarithm of mu square, this thing evolves according to this integral differential equation that if you solve, you know perturbatively, because these functions there are just perturbative, how to go from a given scale mu to a next scale, which is 10 times mu or 20 times mu or whatever you want, okay? So exactly like for alpha S, you have an RG equation for the Parton distribution function. So the scale dependence added by QCD is perturbatively calculable, and you calculate by solving this equation. So these kernels are perturbatively known. I've just shown you how to compute the one at next to leading order, but they've been computed at next to leading order, and now some parts are next cube leading order. So you just keep adding splitting of gluons and quarks out of these lines, okay? It's complicated, but it's possible. And what does it mean? For example, how does the gluon evolve with the scale? Imagine we know the gluon from the SLAC experiments at 2 GeV, okay? We extract it, and then I tell you tomorrow how, as a function of the X. And now we want to know how the gluon changes as we observe it at higher energy. You solve this equation, and you see that the gluon at small fractions carried goes up a lot. So with the scale, you see that it increases between 1 and whatever, 100, okay, as you increase the scale, while instead at smaller values, at larger values of X is depleted. And this is not magic. You just see from this function. So because the probability that the gluon split into a quark, anti-quark goes like 1 over x. When x is small, this probability diverges, becomes really large. So now you understand why perturbatively, whenever you add QCD evolution, you get more and more gluon as you are at small x, because of the perturbative nature of this evolution, okay? And instead, the same thing for, and you have a similar behavior for the quark. Anyway, then we can look at them later on. But you can see that basically, again, even here, you can see that for the quark evolution, when you sum them all up, because of the coupling with the quarks, they become, so grow much less, but still they grow at a smaller x. And they are depleted at large x. While instead for the valence, so this is U minus U bar, okay? So is how much up quark minus the anti-quark, which is the one that we know that is equal to, it has to be picked at 1/3, no? So this should, so U minus U bar, you have 2 of those that should be picked around 2/3, because in nuclear physics we have 2 up proton, and you see that at a small energy, this is peaked around 2/3. And when you increase, the peak goes down because some of the valence quark energy is taken away by the gluon and by the other anti-quark that you put together, okay? So this is telling you how the picture of the quark and the gluon evolves as you increase the energy. To conclude, so if people, tomorrow I tell you how, find these functions and their error at a given energy, it means that by solving perturbative QCD equation, you can evolve them to any other scale. So once you know them at one scale, you know that at all scales, okay, in the collinear picture. That's it. So, and the other beautiful thing, if I had time to do it, you would see it more explicitly, but the interesting thing here is that everything I did for this matrix element doesn't know what happened here. So the Parton distribution functions evolution, okay, everything we said so far is the same here, no matter what happens at the level of the hard scattering, okay? And this is the collinear factorization. So the fact that we can put away the collinear part into a redefinition of the proton, which is universal, is what tells us that no matter what happens here, whether we produce a couple of lepton, anti-lepton, we produce a Higgs boson, the part that we have here at the bottom is always the same. So the structure of the proton in the collinear picture, in the non-collinear picture is much more complicated, okay, is universal. So we have a universality, which is what allows us to do the fit of the PDFs, as I will tell you tomorrow. And I think that's all, and I went over time. I'm sorry about that, and thank you very much.